Perfect. So yeah, if you found your way here, and if you, as you could already see in the last presentation, we have this GitHub page for BART, which actually also already contains a lot of information. If you want to know, if you found your way here somehow and don't know what BART is about, this has like a list of features and stuff, some really small examples. There's also a link to the mailing list if you don't want to go back to the previous presentation. And this is also where you can find the source code. BART actually is archived forever using DOIs. So if you actually have a publication using BART, you can cite it as well. And if you actually want to take a look at the core code, there's also a GitHub link here, which we will get to later. But if you want to know how to use BART in more detail, you can just scroll down on this page and you will find a lot of interesting stuff. For example, if you're using MATLAB, there's a MATLAB interface and examples, which you can find here. For some reason, I didn't open this yet, which just shows you how to do things in MATLAB and how to actually use BART. And there's also previous workshops. So if you have some question that wasn't answered in this workshop, you can take a look there. It will also contain more examples. And there's also the list of reproducible research, which is important in its own right, but I think especially interesting in this webinar, because all of these reproducible papers are also sources of examples of BART in action. And yeah, again, if your paper is also reproducible, and especially if it's reproducible using BART, just send us an email. With that, let's actually look at the GitHub repository, which also contains a lot of very useful things. First, this is only a short README, which is supposed to look nice. If you actually click on the button, README, without MD, you will get somewhere else and you will come into a lot more detailed README, which will also help you install BART on, I think, at least various platforms, at least on Linux, but I will go into more detail on that tomorrow, showing you how to set up your build environment. I think it also includes something about Windows, yes, how to do it there. Where to find, how to actually find your way around this repository, so where different source code is located, where the MATLAB and Python interfaces are located, and things like that. There's also, if you want to see documentation, there's also a doc folder, which contains some text documents. For example, the first one, applications.txt. This is just an incomplete list of papers using BART. But you can just see where BART was used and how many different uses it has. Then there are some of them which are more useful if you are getting more comfortable using BART. For example, BART uses bit masks for specifying dimensions. This contains an explanation of that, but I think we will get to that in, I think Max will explain that. Some things about building and debugging, I will go over that tomorrow. And dimensions, how the FFTs work in BART, because they're, I think, our most important algorithm in MRI probably, and also the style guide, basically to understand in which kind of C style BART is written. There's also another very important document here, which is the references. The first part is just how to cite BART. Again, the list of reproducible publications using BART, but I think it gets more interesting down here, because this contains the references for all of the algorithms and methods that are actually implemented in BART. So if you can see here a list of commands, we'll get to that in a second. All of these commands implement the papers that are below that, or papers for how the FFT in BART is implemented. And yeah, if you actually want to dive really deeply, you can just go to the source subdirectory, which contains the entire source code for BART. And you can just go here and you will also find documentation in all of the functions. Sometimes it's not quite up to date yet, but we will get there. But you can at least read the source code and in that way find out what is it doing. Yeah, I think these are the web resources for BART. So let us go to one of BART's interfaces, which is its command line interface. There are also two others. There's the MATLAB interface I mentioned and the Python interface. I think Max will show both of them just when I'm finished. So if you have a command line interface and you have BART properly set up, you can just type BART and you will see a list of available commands. Some of them are pretty obvious what they do. The FFT just does a fast Fourier transform. Some of them might not be that obvious. So all of them actually take a -h flag to just tell you tell you in more detail what's going to happen if you use this. For example, RSS, it will tell you this calculates the root of sum of squares along the selected dimensions. And then it will also tell you how to use it. You just call BART RSS, you give it a bit mask, more on that later, some input and some output files. And there's also the same things for other things like Phantom has, for example, quite a lot of different options because it can do, not only a Shab-Logan phantom, but also other kinds of phantoms. It can do simulation in k-space and actually do simulate multiple coils as in a parallel imaging setup. And that actually brings us to the file format as well. So this always says, for example, that this has some output file. In which format is this output supposed to be? In principle, BART understands quite a lot of different formats. For example, some raw array format. There's also a cooked legacy format, which was developed, .coo. It contains import functions for some scanner formats, for example, Siemens Twix, and also for the ISMRM raw data format. But it also comes with its own native format, which we call CFL. There is, for example, a function ones, which just creates an array filled with ones. And if we just say it, okay, we want an array with one dimension, that dimension has the length 1, and the output is supposed to be named O, and we look what is actually created, we see it created two files. It created one o.cfl and o.hdr. The CFL file is basically the data, the HDR is the header. So if we look at what is actually in there, we see some information about the data. So the header contains, okay, this is an array, not a multi-dimensional array in this case, but a single dimensional array with only one entry. It was created using the command once and then one dimension of length 1, and the output file name O. It also says, okay, O was the output file and which version of BART created it. And if we look at the CFL, that's a bit more difficult, but we can just do a hex dump. Oh, what? Okay, I'm confused by why that doesn't work. Probably doing something wrong here. Nah. Oh, yep, I can't type. I'm sorry. If we do a hex dump of that file, and people know how floating point numbers are actually implemented, you can probably see what this is. This is the binary representation of a complex floating point number with real part 1 and imaginary part 0, which is what we expected if we create an array of 1. And this is actually also shows you what this CFL file is. It is, and I need to read this to get it correct, it is this 32-bit complex float binary representation of an array in column major order, so in Fortran order, which is also what MATLAB uses. But it's not really important in practice. Why is it that way? Because it's easy to read into memory again. And it's quite nice to have a separate header, that you have the data separated from something describing it. And then let's look at the different dimensions that are used. For example, if we want to look at the k-space phantom, we use the BART phantom command. We say we want it in k-space and we want to simulate 4 coils. We give it some output name. Again, this creates 2 files. And there's also a BART viewer, which I think some of the talks are using. It's separate from BART, but oftentimes used with it. And I can use it now to actually show you the k-space. This is the simulated k-space of a of the Chaplogan phantom, one coil, and there are multiple coils. But I'm not here for images, I'm here for file format. So what does the header actually look like for this? It looks a bit more difficult, or a bit different. So the dimensions now are actually 16. This file actually has 16 dimensions. Why 16? Because the dimensions in BART also have meaning. So normally, if you're dealing with case-based data, the first 3 dimensions are the readout dimension, the first phase encoding dimension, and the second phase encoding dimension for 3D data. Because this is a 2D phantom, the second phase encoding dimension is just a 1. And then the 4th dimension from the beginning is the coil dimension. So in parallel imaging, the different coils will be here. The 5th dimension is for maps, for example, when doing soft sense reconstruction in eSpirit. And the others also have some meaning that might be subject to change at some point. There is like a time dimension, or actually 2 time dimensions if they make sense for your data sets. There is a slice dimension if you're dealing with multi-slice data. Because I don't expect anyone to remember what I've just said, you can go to, if you actually have the source code, it's defined in source, MISC, and then just the header mri.h. And if you look at this, you will see that this is just the definition of the dimensions. 3-dimension, phase dimension, coils, and then some others. And with that, I think that is all I needed to explain for now. I will give it back to John.